Log on, tune in, find out. Another good idea from Cambridge.
Keynote speaker, Tony Chan. We are extremely delighted that he was found time in his busy schedule to come here. He is a foremost contributor to the field of image analysis, numerical methods. In his spare time, he has found time to be assistant director at NSF for all the physical sciences, and now president of the Hong Kong University of Science and Technology. Tony.
Thank you. Okay, it's on, right? Okay. Thank you very much, Adrian, for the introduction. You should really have said that I am very glad that I can find the time. It's not, because it's such a. I've been here once before, and it's a lovely place. It's a lovely part of Cambridge University, and really a pleasure. I also look around. I know only some people. I know less than half, which is a good sign for coming to a conference. Not the usual suspects, and some people I know by name. You finally meet them. So I'm looking forward to the rest of the conference to meet most of you. In terms of the talk, the scope is on the analysis side. So obviously these are things that someone else take the image, okay? Right. And then we process them and we analyze them and so on. So that's the part I'm going to be talking about. Now this, I'm giving you an overview of work that a group of us has been doing for the last 5, 6, 7 years in various parts. There are really two centers, one at UCLA, which I was associated with for many years, and one at Harvard with S.T. Yao, who's obviously most of you know, he's the geometry expert. Okay, actually, let's see. David was a student of Yao at Harvard, actually in computer science, and he's now at computer science at Stony Brook. He has written a book on conformal geometry for computer vision and image processing or something. Okay. Ronald is here, sitting in the back. He will give in a way, the sequel, the second part of this talk on Friday, if I remember the schedule. He was a PhD student in fact, his thesis was on conformal geometry, the conformal part of this talk. Yalin was a postdoc at UCLA, now at Arizona State. Alvin is not here. His thesis was on the quasi-conformal part, and he just graduated a few months ago, and now on his way to UC Irvine. I don't know whether he's there yet. And STL, you know. Okay. So the outline of my talk, roughly a little bit motivation. Why conformal, quasi-conformal? What are we talking about? What kind of medical imaging we're talking about? And then I split the talk into two parts. First part on conformal. This is the older stuff, but I thought I'll put it in context. I don't assume everybody knows that part, so maybe run through that a little quicker, and then focus on the new stuff, on quasi-conformal. I would do the sort of basic of that, and as Ronald's talk will focus a lot more on the various applications. So that part is really broken down into two. Okay, so as I said, the focus, the scope of my talk here, although this work is on analysis, in particular on the analysis of shapes of objects that are derived from images in a medical context. That's the idea. So you know that when the first thing you do when you go to a hospital these days is they take some images of you, various kind, X-ray, CAT, PET, MRI, functional MRI. It was amazing. I have personal experience with this. You go to the doctor, will not do anything before they take some images of you. Okay, they will not do anything. You wonder what they did before, actually, the invention of this stuff. But it's not just when you're sick, there's also developmental things you want to look at. So the idea is to look at the body, your brain, your body. They want to look for shapes, how they develop, look for abnormalities, what is a normal shape, like is there a tumor, is there, and so on and so forth. But the idea is to, in the case of disease, look at, for diagnosis and so on. But there's also a developmental side of it. So even if you are not sick, for example, here is, you can think about following images of a child, from child to adult, over a number of years. And you look at this and you do a developmental analysis as to how different parts of the body, in this case the brain, how it develops. So that's another application. So there are various kind of processing. One is, so let's say through imaging, you get a scan of the brain. Okay, so that's what it looks like. You might want to process that data. For example, you might want to compress the data for later retrieval and so on. So that's kind of processing the imaging data. That's one. The other one is you might have different brains in this case, and you might want to associate them with each other. For example, registration, how to align them and so on. Okay, and then you might want to do. Why do you want to do that? You might want to do statistics on them, because that's how you can tell whether something is normal or something is abnormal. You do data on them, and you might also want to look at shape analysis. You look at, what is a normal hippocampus, what is an abnormal hippocampus, for example. So there are various kinds of things you can do with it. I will, in the rest of my talk, highlight a few examples of this kind. So the question is, why use conformal and quasi-conformal? How can they help in doing this? So here's a sort of overview of some of the possibilities. So typically, a scan like this is obtained from slices, as you can probably imagine. There are many developments in this area. So for example, these are slices of MRI images as you go. And one method to go from here to here is you go and segment. So these are segmentation of these images. And from these segments, you build a 3D model, let's say of the surface or the volume of the brain. So there's some data processing here from the medical image. And once of this is very complicated. As I said, for example, if you want to do statistical shape analysis, you want to compare the right data at the right place, right, rather than mix them together. So one method is to take something like this and map it into a canonical domain. For example, a surface of a sphere. So imagine blowing up the brain in some sense so that it's a sphere, or flattening it into a flat surface. And then you then can register on these canonical shapes, a little easier to do. And then once you get the images aligned, you can then do statistics on them. So for example, in terms of the way you can do this, there are many ways to do that. One literally is like, imagine that the brain is like a elastic surface, like physics. And you expand the brain, blow it up according to mechanical laws of physics. That's sort of one. Well, here we're going to use conformal geometry. That's sort of what we're going to do. Okay, and one way you can do it, go from here to here, is often it involves some partial differential equation. You can imagine an evolutionary process. Even blowing up elastic, blowing up a ball, right? It's like you can imagine a PDE evolving. But even in conformal geometry, which is not physical, it's more mathematical and geometrical. There's also geometric PDE that one solves, and I will highlight a little bit of that, how you go from here to here and from here to here. So that's kind of the idea. So what are these shapes that people are interested in? So let's focus on the brain. I mean, of course, there are many other parts. So the brain is a complicated organ, has many things. For example, deep inside the brain is something called hippocampus, I'm sure you know about. So this is related to Alzheimer's disease and so on. So a lot of neuroscientists and so on are interested in this and the shape of that. There's a lot to do. The other parts of the brain, just highlight one. For example, this part is called the lateral ventricle. So that's also, I will have a 3D picture later on to show where it is. This is sort of like a slice. And okay, so just to show you that there are different parts of the brain that you want to look at. Okay, so a little bit of the mathematical background for the conformal part. Okay, so what is a conformal map? Okay, so you have one, let's say imagine one shape like the brain, and then another space like the surface of the sphere that you want to map it to. Okay, so a conformal map, loosely speaking, is a map that preserves angles. Okay, that's basically what it is. It doesn't preserve area, it preserves angle. So in fact, if you look at it mathematically, so if you map from M to N, okay, basically the metric in the image domain is a scalar, a complex, this is a complex number, a scalar multiple of the metric in the original domain. That's sort of the idea. But more generally, of course, this could be a matrix in a way. It's a more complex. But in this case, for conformal, it's just a scalar. So it's a simpler version of this. Okay, so that's, in fact, this number is called the conformal factor. Okay, and the magnitude of this conformal factor tells you how much the area is distorted, but the angle is always preserved. Okay, that's the idea. So there are many advantages to a conformal map. One is because the metric is preserved in terms of so the local geometry is preserved. Okay, so you don't have a right angle is always a right angle. Okay. So in fact, because of that angle preserving property, you can often define a orthogonal grid on a very complicated surface, like the surface of the brain. Okay, so you can impose, for example, you can derive an orthogonal grid on this, and the way you do it is you map this into here, and then you impose an orthogonal grid here, and you map it back, and you get this, and all the right angles here are preserved here, so it's an orthogonal grid. The advantage is that you can do many data processing on an orthogonal grid, like solving PDEs, for example, a lot easier than on a complicated surface. The other advantage is a little bit less obvious, and that is because of this, there's a scalar multiple. The transformation in the metric is that lambda is a scalar multiple. I'll show later that means that if you have a PDE, a complicated PDE on the original surface, defined on that surface, the transformed PDE on the image domain is actually quite simple, quite simply derived from the original PDE. You just have that lambda floating around somewhere, rather than a whole, every term mixed up, all the partial derivative all mixed up. So the idea is that if you have, let's say, Navier-Stokes equation, you take a Navier-Stokes equation on one side, the other equation looks like Navier-Stokes. And you can adapt, let's say, a Navier-Stokes solver easily to solve that. Okay, so that's another advantage from a practical side in terms of solving these problems. Okay, so how do you compute conformal maps? That's so there are various cases. Okay, so for example, for genus 0, so it's just let's say a ball-like domain, and it's the simplest case. When you have higher genus, it's more complicated. But so I don't want to get into that detail. Let's look at genus 0 first. Basically, a conformal map can be obtained in the genus 0 case by minimizing harmonic energy, which reduces the solving, Laplace equation, basically. That's roughly what it is. Harmonic is the same as conformal in the genus 0 case. So over here, so imagine the surface of this complicated shape is represented by like a finite element mesh, right? Triangles. In fact, that's how they are constructed in the earlier slides I show. Okay, so you have that, and you can easily define sort of discrete analog of the harmonic energy on the surface. It is a typical standard case in finite elements. Although this is on a curved surface, but you can define it. For example, this harmonic energy is just you have edges, you have function value on the edges. You do the usual L2, and you sum up over all the edges. That's sort of the typical thing. So you can write this down, and so the idea in the map is, where do these vertices go, right? When they have map, and you can find out the F, the map, by minimizing this harmonic energy. So imagine this involves solving some sort of Laplacian governed equation on this set of triangle mesh. That's the idea, and there are many techniques for doing that. Yeah. So, for example, here are two brains of the same subject at different times. Okay, by doing what we did before, you can map them onto the sphere. Okay, and without getting into the detail, you can then register these two. For example, there's some degree of freedom. You can line them up. The doctors are very good at, when they look at your brain, they can look at these ridges and valleys, For example, I think in the middle of our brain is a sort of deep, you all know about left brain and right brain. So there are these two halves. And the doctor can automatically align them, at least in that direction. And then there are different landmarks that the doctor look at, and they can, so the use of landmarks in aligning, in registration is also a key thing in here. So the idea is then you look at these two brains and you try to align them and maybe do statistics on them. So the idea is these two are good parameter domain. You can do various things on them. Now, how do you more generally compute these maps? Okay, so imagine, as an example, you have this brain surface, and you want to map it to the surface of the sphere. Okay, one way you can characterize that is to say, this original surface is very complicated. It has high curvature and low curvature points, right? These values, these folds have high curvature. So you can look at the curvature of the original thing. And the sphere, can be characterized by saying that the curvature is constant, right? It's everywhere. It's uniform across. So in a way, you can think of this mapping as going from a surface with known curvature, very complicated, and mapping it into a surface with known curvature, so simple, like surface of a sphere. Or in the case of the flat region, the curvature is 0, for example, right? So you can sort of, these canonical spaces, a simple characterization of the curvature. So you can imagine a flow, a PDE actually governed by a PDE, that flows from a given curvature to a designated signature, a curvature. That's the idea. Okay, but of course, when you do this, you have to guarantee that it's conformal, that mapping is conformal. That's the key. Okay, so one way you can look at that is you look at the metric of the original domain as G, and one way to guarantee that that is conformal is that you look at the map to a metric G bar is related to G by this. Is e to the some factor, in this case it's 2u. When you write it like this, it's guaranteed to be conformal. Okay, so then the idea is that what is the u? So the mapping is characterized by u, and you want to derive the equation in u. Okay, that's the idea. So the way the typical curvature flow is like this. So you want to flow from k to k bar. Okay, so you want to have a flow equation that flows it according to the current metric G, and the speed is related to that, how much you have arrived, right, at the designated curvature. So this is like the speed. Okay, how much k bar is different from k. So as you get close to that intended domain, then the speed slows down, and at the end you just when this is 0, that means the two are the same. So that's sort of a typical flow equation. Okay, and if you plug this into here, the G, you get an equation for u. So this is the equation we solve. It's called a Yamabe equation, and so you solve for this u. It's very, flow this equation, and once you have that, you can compute the G by plugging back in there, and that's how you get the map. Okay, so that's sort of the idea. There's is one way to do it. It's not the only way. So to give you an example of that, I want to go through this part more quickly because it's older stuff. So imagine this is the front side, one side of the brain. This is the back side. Okay, so this is I think it's the hippocampus, if I'm not a doctor. Okay, so and these are landmarks. These are ridges or valleys that you have identified, that the doctors, physicians have identified. So in this case, there are 5 of these. There's 3 on this side, and there's 1 here. There's another 1 here. Okay, so you want to, let's say in this case, you want to map it into a flat domain. So curvature equal to 0. Okay. So one way you can do that is you look at this. This is an important object with a shape. And you say, I want to map this onto the outer part of this disk, where the curvature is constant, right? Curvature is constant. The other one, you can imagine you slice them open, and you also specify that they have to be constant. So each one of these 4 landmarks correspond to one of these disks. Okay, so you can imagine slice this open. Okay, that becomes the outer circle. You can imagine. And you want to slice them open, and you want them to be little circles. And the size depends on the map. It has to be conformal. And you use that flow equation, and you map it, and you get this. Okay? So is that, you can kind of imagine, literally, if it's an elastic surface, you slide them over and you pull them apart. But all this stuff, when you pull them apart, has to be conformal, and it's done in the way that I outlined before. And this is a similar example with 7 landmarks. So this is a different a brain with different landmarks, and you see depends on where the landmarks are, the disks are different. Okay, so you can imagine now if you do this, it's probably easier to line this up. You can imagine this hippocampus is always on the boundary, so that's sort of it's fixed. And the size and location of this little holes is going to characterize what the brains are. Okay, right? How to register. You can imagine that you can do that. Okay. So some applications. So here's an example where you can map it onto surface of a sphere, or you can map it onto a flat space. Okay, so there are two different things here. So so here's a case for registration. I hinted at that. Okay, so again, this is one side of the brain. This is the back side. In this case, there are 4 landmarks: A, B, C, D. I think you can see more or less. I hope. Okay, A, B, C, D. And in this case, the A landmark is mapped onto the outside, and the D landmark is mapped into the middle. And then the other ones are over there. So you're taking these two using the method we have. You map it into this. Okay. Now you take another brain, and you do another map, and you end up with this. Okay. And then there's some technicality that you can align the center of this hole, align the holes into the center of the disk. There's something called a Mobius transform when you do this conformal map. So there's 3 degrees of freedom that you can do. So you can align these things. And so now you can imagine a whole population of brains like this, right? With a hole in the middle. The size may be different. And you have landmarks here. And now you can see, you can define many people here work on image registration for images. The images are flat, right? And you can sort of align. For example, you can imagine, you can define a functional for registration where you want this B to be close to the B over here, because the doctor said those two should be similar part of the brain. So you want to align them so that they are matching as much as possible, for example. So you can define registration algorithm that way. And this is just another example. Instead of mapping onto this, you can also map it onto a horizontal rectangle. The way you can imagine this is to take this and put a slice across here and unwrap it, and then it becomes a rectangle. Okay, so for example, the A is in the bottom, right? And the D here is slit open. So you just take it here and you wrap it out. And so you have that. And maybe this is easier because you might have a registration code algorithm for a rectangular domain, and you can do registration that way over here. And all this time is conformal. That's the idea. Here's another way I hinted at. This is another application. Imagine you have a PDE on M, on the original domain. You have a PDE. By the way, that PDE could be related to processing data on the original surface. I'll give an example. But it's very complicated, right, on this, let's say the brain. You want to solve that PDE, and you want to transform it after this mapping onto a PDE on this PDE on the canonical domain. And you want it to be simple so you can easily solve it. Now, using conformal map, you will get it. For example, this Navier-Stokes type equation on the original domain. After the conformal map using the conformal factor lambda, it's transformed into a Navier-Stokes-like PDE with the lambdas floating around in these two terms. Okay, so it's relatively simple. Okay, for example, even if the area is not distorted very much in region, the lambda is close to 1. So in those cases, actually, they're very much like the Navier-Stokes. When things are distorted a little more, this is the deviate from 1. Now, so this is basically because the basic differential operator like gradient and Laplacian and so on transform, like just with lambda as a scalar on the outside. More generally, if you have a general parametrization that is not conformal, you have very complicated, basically instead of something like this, which is a diagonal, a constant times the identity, you have a full matrix, right, in general, and it's very complicated, cross derivatives and so on and so forth. So with conformal, the beauty is very simple transformation. So for example, I'm sure some of the speakers will talk about image processing. For example, here too, you can denoise. You can denoise data, let's say intensity data on a complicated service. Okay, for example, you use, this is Rudinosa-Fatimi, ROF model, many of you know, TV and so on. So you can define a similar thing on the surface. Okay, so this is all with the S here on the surface. You can define that. So you have if you do the Euler-Lagrange equation here, you get a PDE on this surface. Okay, so you blow up this dot onto the surface of the sphere, and the PDE there looks almost like this, except with the lambda here. Okay, so the same code that we have for doing ROF, I'm sure many of us have such a code. You can easily adapt to solving. So here's a denoised version of this, using the same code basically, slightly modified. This one. Another application, I don't know whether people will talk about this, is in painting. So the idea you are missing pixel values and you want to fill them in. One application where you have like these domains, it says I'm ugly, and you want to fill them out, okay? And so you can actually get them back, and the idea you want to respect edges, and when you have noise, you want to kill them off. When they're edges and so on, you want to preserve them. And so they also sort of related PDE on the surface. And again, that PDE just have some lambda. Well, in this case, you have a lambda here and a lambda here, with the square root lambda. But again, the in-painting code that you have can be easily modified for treating images to now treating complicated images on complicated surfaces. So that's another advantage of this. Okay. So you can anything you can do on a standard image processing on a flat domain, you can now do on surfaces by doing this conformal map. That's the idea. Here's a segmentation application, which is related to medical. I mean, it's not just made up. So remember those landmarks, okay, that I use for doing, well, how do people find them? Well, the doctors, the brain surgeon know, right? They look at the brain and they say, okay, I recognize this. They probably have Latin names for each one of these, which I don't know. But, as a toy example, mathematically, you can define areas of high curvature, okay? Because those correspond to somehow some geometric features. And you can actually try to automatically identify those things and offer those as candidates for the physician to look at. So this is very standard for image segmentation, okay? Now in the standard image segmentation, the segments are defined by features, vectors, right? Could be intensity, could be color, could be texture, and a segment, a region that you want to segment is defined as region where those features are more or less the same, okay? So in this case, you just have to find the right feature, and the feature here is, let's say, curvature, okay? Let's say mean curvature, okay? Mean curvature. So the IF, which typically is image intensity in segmentation for flat images, here you just define to be areas of mean curvature, and the rest, for example, this is a method that Luminita Vesey and I developed many years ago. So you can sort of do that, okay? And you can see that it evolves like this, okay? You have a brain here, you want to identify this, you start with something, that segment sort of grows, and at the end you get that. So you identify that area of high curvature, okay? You sort of see, here's another example. And the topology can break up, and that's the feature of this method. You can sort of identify things like that. All right. So again, I want to emphasize, it's not this model that we ever, you can have any model, your own favorite model. The idea is you probably have some algorithm on the flat surface, and you want to do this on the brain, and you take this, map it onto this, you run your usual thing, you identify this thing, you map it back, and you have those landmarks. That's the idea. Now here's an application to do a shape analysis, okay? So this, I think, is the lateral ventricle. Am I right? Yeah, okay. So this shows you where they are in the case of a human brain. There are two pairs of these somewhere deep inside the brain. So this is this is the front side and back side of the same, okay? Of a healthy individual, and this is someone with AIDS. Actually, when I first looked at this, I thought this is the person who's sick, Okay, but the smaller the better in this case. I mean, I don't know, somehow swollen, I guess. So we have some sort of algorithm which identifies certain points, and I don't want to get into that. For example, you want to compare, the idea is that you want to compare this shape with that shape, and you see how much this is abnormal compared to this, right? That's the idea. I mean, you can see it is different, right? One is swollen for one thing. So the way you do it is, but you see certain thing, right? There's this branch, there's correspond. So you want to sort of pin them down. And the way we did it was we identified like this point, this point, okay, and then corresponding over here, and the same thing over here. So identify those points, and they have to line up. And once you have them, then these ridges are defined automatically through some geodesic definitions. Okay, so I don't want to get into that. So the idea is that once you have these points, you can define the segments. Okay, so that, let's say that's defined. So now the point is you take this. Now you want to compare this segment with this segment, and you want to see how different they are. That's the idea. So the way you do it, let's see, is that you take this and you map it conformally, in this case, to a rectangular region. Okay, so using the method I used before. So, this purple one is mapped into this. This gold one, which is like here in the back of this, is mapped into this. Of course, they share a boundary because you can see what they share a boundary here. So there's 6 segments of these, and they're mapped into these 6 contiguous. By the way, the aspect ratio of these things are key. Okay, that has to relate it to the shape. And you take the similar thing over here and you map it into 6 different strips. Okay, and so the idea now, if you look at this, and bearing in mind that this aspect ratio sort of tells you about the conformal similarity or dissimilarity. So then you look at this and you say, well, something, this is so much elongated. This must be quite different from this, and you can do some quantitative analysis to how they are different. Okay, and you can tell if this were more like this, then this would be more like this. Okay, so you can then easier to do the quantitative analysis of the shape. Here's another example of some other disease called Williams syndrome. Okay, so here's a healthy patient's brain, and here's this is a patient's brain with this syndrome, and you see some landmarks. You can barely see them in this light. So you use the technique that we used before. You map it into a disk, and landmarks are mapped into this little holes, like Swiss cheese. I mentioned to you this Mobius transformation degree of freedom. So you use that degree of freedom, and you take one of these, let's say the bigger circle, out of this, and you put it in the center. So you sort of register it that way, and you do the same thing over here. And then so the idea is, if you want to tell how different or similar these 2 brains are, you then look at the rest of these, right? The image data, where the holes are, the size of the diameter. That would tell you a little bit how these 2 are different. And the idea is that it's a lot easier to do it over here than to do it in the original domain, because it's so complicated. That's the idea. So the conformal dissimilarity is measured by the location and radii. These are the circles. Okay. All right. So that's the older stuff. About 10? 12 minutes. 12. Okay. More generous. Give me 2 more minutes. Okay. So I want to go to the second part about the quasi-conformal. Okay. So that was all conformal. Okay. So what is quasi-conformal? Well, conformal means preserving angles. Quasi-conformal is almost preserving angles, but not quite. Okay. So the simplest way to think about it is, a circle in conformal is mapped into circles. In quasi-conformal, they map into ellipses. Okay. And the deviation from a circle, both in terms of elongation and the tilt, the angle, is measured by a complex number, mu. Okay, the magnitude of mu, the deviation of mu from 1 is the change in area, and the angle, argument of mu, is the angle. Okay, so that's roughly the geometric idea. Well, mathematically, the equation is this. So F is the mapping, Z is the coordinates, and in the conformal case, df dz bar is equal to 0. Okay. Okay, so that's the conformal case. In general, you have this relationship, and this is not equal to 0. Okay, so and this number, like the conformal factor, is a complex number, and this one is called a Beltrami coefficient, and this is a key thing that we're going to use. Okay, in it. So mu is deviation from 0, measures the distortion from conformality. Okay, so that's the idea. So, so here's an example. So you take this surface, in this case a face. So when you take you put some circles here. In a conformal map, this circle will map into circles. But in a quasi-conformal map, these is mapped into ellipses. So you can see them. And in terms of the metric I mentioned before, in the conformal case of this lambda, in this case you have this more, so the mu comes in here. Okay, the mu comes in here. Okay, so right angles, map into right angles in that case. Now, so the idea of using quasi-conformal rather than conformal, is it conformal sometimes in medical application? It's too restrictive, okay? Because there are things that the distortion could be non-conformal, okay? So of course, you can look at general diffeomorphisms. You can just say you have something to map with something, but that's almost too general, okay? So the idea is that there are situations, the proposition is that there's a situation where you want to look for deviation from conformal, and that if you can relate it to medical diagnosis, that would be useful. And there are certain cases where that is the case. It's not always, okay? So I'll give some examples of that. But before we do that, I want to establish an important mathematical fact. And basically that is this Beltrami coefficient that I mentioned before, the mu, okay? It's basically tells you everything about the mapping. So in other words, if you have the quasi-conformal mapping, there's a corresponding mu, right? How it distorts circles. But vice versa, going the other direction. If you have the mu, the Beltrami coefficient, you can derive the map itself. See, the idea of the Beltrami coefficient has certain advantages because it's just a complex scalar. And the only condition you need is that this magnitude of this scalar be less than 1. Okay, that's all you need. Whereas with the coordinate transformation, you have to be a little bit more careful when you map the coordinates, that when you process them and so on, they correspond to a real map. For example, there's 1 to 1 and the Jacobian is greater than 0 and so. I mean, it can be done, but this is actually, it has some advantages. So basically, this theorem says, if you have a map F mapped to this from one surface to another, and you fix 3 points. These 3 points map into these 3 points. Then once that's fixed, then that map can be represented uniquely by a Beltrami coefficient. So it's 1 to 1. F is the same as mu. You have mu, you have F, you have F, you have mu. Once you have this. And that gives us a lot of flexibility in terms of computation, storage, processing, and so on. Basically, we want to deal with mu rather than F. That's the idea, okay? It's similar to like processing surfaces using implicit representation level sets. Right? Every time you have a level set, you have the surface, but you want to process it here has many advantages. You process it here and then you mean something. So in this case, it's analogous. Anyway, now going from one direction is easy. From the definition, you remember df dz bar is equal to mu times df dz. So mu is just the ratio of these two things. So if you have f, you can compute mu. Right? You can just, you can approximate these on the triangular mesh and so on, you can compute mu. So that's relatively simple. So here's an example. Let's say you have a map from this brain into this brain. Okay? And so you compute the f, and from the f you compute the mu, and this is the mu. This is a Beltrami coefficient. Red means higher in magnitude. Blue is lower in magnitude. So you can sort of see that there's more distortion over here and less distortion over here. You can sort of read it that way. Okay? So now you have the mu. You can, using the technique we'll show, you can reconstruct this surface. Because once you're here, right, well, you have the f, and using the f, you can map it back here, and you're supposed to be able to see that this is the same as this. So you don't lose anything. That's the idea. Okay, so how do you, now I want to compute the other way around. That is, if I have mu, if we all agree that mu is good to have and easy to process, once I have the mu, how do I compute the f back? Because ultimately I want to have the map, not the coefficient. So there's several ways, and Ronald would talk about one way. I'll just briefly outline one way. We call it Beltrami holomorphic flow. It's a fancy name. But basically it's numerical continuation. Okay? So I have a mu. Okay? I want to compute a corresponding f. So I know I can start with 0. 0 corresponds to conformal map. Okay? So the idea is I take small steps. I go from 0, a little small step, and go to my mu. That's the idea. Okay? So I need I need a formula that tells you if I change mu a little bit, how much does f change? Okay, and so this is what this theorem tells you. So this says if I change mu, according to this expansion, t is a small parameter. This is a high order term. Okay, so if I change mu by t times nu, how much does the corresponding f change? And it tells you it's here, and this f dot can be computed. It's a little complicated formula, but okay, it can be computed. So you can, this is analytical, you can compute this. Okay, so basically the idea is you start with mu and you do mu over some big n, and you take n steps and you update this. You have a little discretization error, of course. The smaller the step, the better it is, because you have these high order terms. So this is like an ODE, right, in some sense, and you can do it that way. So these are some examples. This is a surface, the checker point just to show the distortion. Mu equals 0, that's a conformal map. Okay, so we put circles here. And now these correspond to mu equal to different values. So mu is given by this, and the z0 is, given here. So there's higher distortion, lower distortion, and lower yet distortion. So this is a simply connected domain. It's like a mask. So you can sort of map it into a surface. And so you have mu, and you compute a corresponding map, and you can see, right, the distortion here. And the idea here, this example, is show that you can do it with multiply connected domain. Okay, same thing over here. Corresponding to different mu's. These are synthetic examples. So I'll show you a couple of examples, and I'll finish with that. So now here is a registration application. So this is the hippocampus. I think I showed before, it's deep inside the brain like this. Now hippocampus it's different from the cortex, the outside, where you have many different folds and very distinct landmark. Hippocampus is like a little, I don't know, like a tooth or something. Okay, it's in fact it's smooth, and it's relatively difficult. I mean, to see, you can see there's a sharp end, there's a blunt end. That's about it. Okay. So the idea is that you have these two, and you want to, let's say, match this with that. You have to register them. Okay. So of course, one way you say, okay, how do I use a map to map from here to here? And I allow, let's say, deviation from conformal. So one thing, I want it to be close to conformal. So I want a map that minimizes, let's say, this non-conformality, which is this. Okay. But of course, if I do that, the best way is to do, easy way, mu equals 0, that will minimize that. But if I do that, then maybe this would not match that as well. And it turns out a good way to sort of compromise between matching the shape and deviating from conformality is to balance these three things. So you have we use two terms that measures the deviation of both the mean and the Gaussian curvature of these two surfaces. Okay? So you basically, you want this shape to be about the same, but you also want it to be least deviation from conformal, represented by this. There's a trade-off between this term and these two terms, right? Okay, so that's the idea. Okay, so this is not different from many segmentation algorithms. This is what you have. Okay, you want like a smooth shape, minimal surface area, but you want to match data. It's a similar thing. In this data, because you want to compare shape, is curvature. Okay, in that case. Now, what it turns out, this is actually a little bit more than that, and you can prove a theorem that says the two shapes are identical if and only if this energy is equal to 0. So this is actually the right measure. Okay, this mix is kind of the right measure. Okay, you know, if you just have the conformal map, it doesn't tell you that. If you just have the curvature, it doesn't tell you that. Because if you just want to match the curvature, you can just force this to be that. But your map is very general. Okay, and if you have conformal, then you don't match the curvature. So this combination is sort of the right thing. So this is a complicated slide that says if you want to minimize that term, that Beltrami plus curvature, you can do it all in terms of mu. The idea is that these curvature can all be written in terms of functions of mu. Okay, that's the idea. So you have a one complicated functional that is in terms of mu. You want to minimize that. Then you can do your usual thing. You can compute the Euler-Lagrange equation of that functional with respect to mu. You can do it. So this is not to look at the detail. This is doing the Euler-Lagrange, and all these curvature terms can be written out, and you have some. So here, in some sense, is the Euler-Lagrange flow. Right? The flow for the curvature term is just mu because you have the square of that. And the curvature term gives rise to something like this. It's actually not so complicated. Okay, so you can sort of use this Euler-Lagrange flow to compute the match. So here's an example. So you have two hippocampus. You want to best match this to this or register it. So this is the progress of the iteration. This is the total energy. So when you do a flow, of course it goes down. The energy goes down, and this breaks up the two terms. This is the curvature matching term, and this is the conformal term or the non-conformal term. You start with conformal, there is 0. So you allow it to deviate from conformal, so that goes up. When it goes up, this goes down, right? Obviously you match better, and then somewhere depending on the parameter you choose, you settle down on a minimum. And that corresponds. So this tells you the energy, okay, at the end. So red is high. So that means at the end, this part of the shape is least alike. Right? You can think of it that way. So it tells you where. Blue is where they have good match after this match, and the red ones, they're like here, here. So over here, they are, even if you squeeze it, they don't quite match up. So it tells you a little bit. In fact, once you have this index, this is a field value, right, over the space. You can, oops, did I miss something? I'm a step ahead of myself. So that was for the hippocampus, and here you can do it on the surface of the brain. So here's an example where you see you have the same patient over different times, okay? You see this one blown up. This is thicker than this if you are a trained physician, okay? I can't tell really originally, but this is a little thicker. You can see here, it's thicker than this. This value is a little narrower. So the idea is that this is a complicated thing. You want to automatically do that, okay? So the concept here is that this thickening is the deviation from conformal. So you want to identify that automatically. So you do this. So in this case, you take this. You want to see how this is mapped into that. So you map these both into flat spaces, and you register them, over here. Okay, so I don't want to get into too much detail here. So the idea is this. So imagine you do that to this surface, not the brain now. This is the face. Okay. If you want to just after the map and onto the flat surface, and you plot, and say this is a very standard metric. It's called an isometric index, which is deviation from the identity. Okay, that's the idea. And you see that you would not. You see different peaks, and you have to find where the things are. Now here you have a thing where you have, let's say, a bump, a big pimple, okay, and the rest you map into this, and you want it to be conformal. And this bump shows up as a peak. So when you look at this map using that index, you clearly see that this part is the larger deviation from conformal, and that you can see is an abnormality. That's sort of the idea. And this is, so the idea is that this is I make this in my last slide maybe. So you have this plane, you have these two areas where they are distorted, and you run through this test on the square domain, and these two parts shows up. So you say these two parts, there's something abnormal in the sense of deviation from conformality, and they correspond to actually these two parts, and you see they actually are different. Okay, this is just defining an index. So if you have this index over space, you can sum them up over the whole brain, and you have an index. You say how much is this brain different from this brain according to this index, so you can sort of do that. I think I have one more example, but I'll skip that. Yeah, I'll skip this part. Okay, so this is a few slides. Okay, so thank you.
Thank you very much. Questions? Yes, Bill?
Yeah, so early on you said in the continuum case, in 2D, a harmonic map is the same as a conformal map.
Yeah, minimizing the genus zero case. Yeah.
And then for the discrete case, you defined a discrete harmonic map.
Yes.
Is that therefore discrete conformal in the sense that it preserves angles?
Ah, that's a good question. Yes. Yeah, that's a good question. Ronald, do you know the answer to that? So is it discrete?
I'm pretty sure it's not. But
Yeah, yeah. Well, so at least you have the up to the discretization error you'll have, right?
Or maybe
But the
what I
question-
mean is there's a different way to be conformal, discrete conformal.
I agree. So yeah, exactly. So I've been thinking about that up to a discretization you have it, but whether there's a discrete version of that,
Yeah, okay.
yeah,
We'll talk
I
later.
haven't seen it. Yeah.
Marty?
Well, I was also asking, can you measure the stability of how one measures the stability of these imaging maps? And are these, when you have a brain and you make the initial discretization to triangles, how sensitive it is to the size of this discretization of the original surface?
Oh, I don't think we've done an analysis, but you know it should be very stable, right? You have harmonic energy and so on. You know, those are things we know a lot about. You know, we kind of, from our practical experience, they're very stable. Okay. So you know, they are elliptic in some sense, right? So it's relatively stable. Yeah, it's sort of naturally dissipated, right? So small thing would not affect things. Yeah. Mario?
Well, if you prescribe initial and final curvature, I think there is a certain degree of freedom in the choice of the conformal map.
Yes.
The conformal map is not unique.
Yeah, there's you know, the Mobius.
The Mobius
yeah, Mobius
transformation.
transform.
So does this make a difference at all, or do you have a criterion for taking?
No, so we use those degrees of freedom. Sometimes when we move the disk to the center, and you know, for example, in registration, you want to use that. Right? You just when you want to register two brains. Okay, so that adds to your degree of
You have
freedom.
to register in the same way,
In the same way, yeah.
right? But does the way change things? I mean, a different choice of the Mobius parameters. Does it
No, I
change
would say
anything at all?
you usually when you register, you have some data that you want to match, right?
Okay.
Some data you want to match.
Sure.
So in addition to matching those data, you use those three parameters to give you the degree of freedom to match them. You could have you could have data on the server, you can have landmark data, so all that you want to match, that's how you register. So how do you move them in order to do it? Well, that you use the Mobius degree of freedom to let you. So you imagine let's say on the disk or on the sphere. The sphere you can have, you know, sort of some rotation that will allow you to use that degree of freedom to do the matching. Ronald, you want to add something?
Yeah, so usually when we do the registration, usually we have that landmark feature point. So this landmark feature point actually can solve that Mobius transformation as we do it.
Thank you very much.
I have a
She's
question about,
busy. I might not.
I have a question about general idea. I mean, why this kind of transformation? Why not mass-preserving transformation? Aren't they supposed to be better?
Oh, why conformal? Why?
Conformal.
Yeah, that's a good question. I have a. Some people have studied this. Now, it's not true in all cases. I would be the first to. But there are people. In fact, there was. I don't want to. I can show you offline. There was on one of the slides. I have a little reference. Okay. So people have studied. So in some cases, in certain cases, this conformal map actually makes sense in a medical sense. You're right. So otherwise, mathematicians love the mathematical idea, but they don't always apply to the particular class of disease. So I would be the first to say that you don't want to use conformal in all cases and assume that will work, right? That's basically what you were asking. But there are instances, and there were some examples, citation I put in there.
So do you have some comparison to other methods?
Yeah, so we work with the people in the neurology department at UCL Medical School, and they have a huge database, and you know they do this. it's so I have to rely on the expertise. So as long as they're willing to collaborate with us, I assume that this stuff is has some contribution to that field. Yeah, but it was
I have two questions. The first one is from clinical viewpoint. I have hard time to imagine a physician looking at conformal maps. So I have hard time to imagine a physician looking at this representation because they're not used to. So how do you get around that? How do you convince physicians to?
Well, you convince them by actually showing that this makes a difference in the diagnosis. I would think, not the mathematics.
They cannot. They have to understand what they are doing, right? That's a key point there. And if they don't understand what the measures they get, it's really hard for them to.
Well, so
at least that's my experience.
Actually, I have a personal opinion. Okay, first of all, you can explain that conformal is easy to explain preserving angles. That's very intuitive. Okay, it doesn't preserve area. So at that elementary level, they do. But on a personal level, I found many doctors, they actually, when they process, they look at so many data, right? PET, MRI, they don't all understand the physical origin of this. But my sense is in their training, they've looked at how to interpret the result from experience. And they actually, that's how they build their expertise. So ultimately, you do all this stuff. This only gives them another option, right? This gives them another option. You map like this, you have this, and they look at how this applies to the disease. And when they incorporate in the medical training, the radiologists really, when they look at this, they see that's how they do. But it's not like they have to understand the mathematics or even the physics of it before they can do it. Even most doctors don't, which is kind of scary actually to think about it, but that's the fact.
And when you do this mapping, usually you don't take into account that parts of the surface are more important than other parts of the surface. I mean, so when you look on the brain, there are some areas which are more important than other areas.
Yeah, in this we have not.
So if you want to integrate this information in this framework, is it feasible or?
Yeah, I would think so. For example, if you think certain part is more important, you can introduce it as a weight in your data matching term. I mean, that would be a natural thing. For example, just as an example, right? You say, I want this to match better than this other part. So that's like a weighted norm, right? And it's one way to do it.
So my question is pertinent to Nikos's question. So once you identify all the key differences in the mapped space, is it possible to come back to the original space, just highlight the key differences, maybe zoom into the area of interest or use pseudocolor or whatever?
Yeah.
To allow physicians to have a more intuitive view of the key differences.
Yeah, that's the whole idea. You can go back and forth.
Right.
Like I show example where you do things over here and you come back. Yeah. What I mean is, I guess we as mathematicians, we are half a step removed from that. Okay? You see what I mean? We work with mathematicians, computer scientists in the medical school. And they interact with the actual people in the front line diagnosing those diseases. We work with them and say, okay, if you are interested in this part is more important, then we can incorporate it. But you're right, ultimately this has to be a continuous chain, working in, ultimately the test of success is whether it actually helps with the diagnosis. They're population studies. So it's very quantitative, right? They say, if you have this, how do you differentiate? Whether this is actually a modality that differentiates, let's say, abnormality from normality, ultimately. So they have a way to tell. We provide them with an extra toolbox that they can use.
Okay, I think people are ready for coffee. Thank you again very much.